Great.
Okay, welcome to Finite Methods. We'll be covering an example for a spring problem. And just to remind everybody, the idea is to take a structural system, which is could be 3D or 2D, and obviously if the structure only can stretch, then it makes sense to idealize the body so it's easy to solve, so you don't have to model every single thing. That's the whole point of finite elements, is to find ways of idealizing the physical system in a way that you can approximate the solution. And then you have the local element behavior that we have developed. And we came up with the formula here that you see, and that was developed using Hooke's method, Hooke's equation, which is the constitutive law. We use the equilibrium equations and the equations of compatibility. Then we describe how to create the code numbers to be able to solve the problem. So Leonardo, here's the
Okay, so the problem we're gonna solve. Let's say that we have a sheet, right? The thickness of the sheet is 1 inch, and the rectangular space is 10 inches by 16 inches, right? It's made of aluminum with Young's modulus 10 MSI and Poisson ratio 0.3. You can see that there are two cutouts with dimensions 2 inches by 12 inches, right? And this structure is subjected an unknown load, but this unknown load should guarantee that the integrity of the structure. So if the strength of the material is 50 KSI, and we have a desired factor of safety of 1.5, we need to solve for that load. All right. Okay. So as Professor Goyal was mentioning, in the direct method, the first step is, let's start by this, right? We need to idealize the structure by springs. So each spring will represent different segments in the structure. So if we start from the clamp end of the structure, we can draw the first spring on the top, all the way from the left to the right of the cutout, right? We could do that, right? We can keep going with the same representation of the spring. We can so yeah, exactly. We have that spring representing the top, then we have another spring representing the middle, and one more representing the bottom of the last.
But we could use symmetry so we can model half.
Yes.
So that reduce the numbers of degrees of freedom.
Right. I mean, it's true. But I mean, if we don't want to use symmetry, we'll have 3 springs on that side, right? And we have one more spring connecting to those 3 springs. So we'll have a total of 4 springs, right?
Right.
That would be one way to do it. Now, if we use symmetry, we can reduce the number of springs only to 3 springs. And the difference and each spring, the stiffness of each spring will rely it depends on the area of the structure or the segment that is representing, right? The Young's modulus is the same for all the structure, right? So it doesn't change. And the length of the segment that the stiffness that the spring is represented in the area is also could vary. All right. So let's start by this. make a sketch of one spring. If we make a sketch of that one spring, we identify one node, which is the dA with displacement di, and we have another node at the end represented by the displacement dj, right? That's for each spring. On the node I, on top of the displacement, we have also a reaction force, Ri, which is represented by the arrow going pointing to the right. And also we have an internal force, which is represented by Fi, right? In the other node, we have a similar thing. We have another force, internal force, Fj, and some reaction, possible some reaction, Rj, right? The stiffness of the spring, which is the stiffness of the element, is represented by the formula Ea over L of each element. And if you want to do it in this matrix form, it will be represented by this 2 by 2 matrix, which when you multiply the displacements should be equal, right, to the forces in the spring at each node, Fi and Fj. All right. So that's at the level of each element. But the first step, but before that, we need to identify what are the active nodes in the idealized model. So if we start from the left to the right, the clamp node has zero displacement, right? That's the condition. We don't have any displacement at that node. So let's call that one D0, just to say something. The node J for either the element 1 and element 2 could be the first node or active node. So it has some displacement. That displacement is one of the ones, it needs to be calculated by the in the problem, right? The node I of the springs K1 and K2 is the node J for the springs K1 and K2 is the node I for the spring K3. So it means that the same displacement happening in the nodes J for K1 and K2 is the same displacement for node I in K3. If it does not happen, we have a discontinuity in the displacement, which physically is not possible for the structure, right? So we need to guarantee that. All right. So the last active node is the node J for K3. So actually, we are solving for two displacements in this problem, because for D naught, we know that displacement is 0. What we don't know at D naught is the reaction, right? That's what we don't know.
One of the questions that the team has is that the problem statement states to use 4 springs, but if you find that there's a simpler way using symmetry, you should go for it. Don't listen to what we're saying. So if you can make it easier, it says 4 springs. We're using 3. 3 is acceptable because it's faster, right? So you should take advantage of that.
All right. So so now for each element, we define the stiffness, right? Remember that if you're using symmetry, the stiffness of K2 will be different with respect to the stiffness of K1, right? The area is different and the length, but the length is the same, but the area is different. Just keep in mind. So once we calculate the three the stiffness for each of the element, we can go to the which are pretty much the local stiffness. We can go to the global stiffness and put all together in a matrix. So the area for the first element is 2 by 1, is 2 inches by 1 inch, right? The Young's modulus, we have the information, and the length of that is for 12 inches, right? 12 inches. For the second element, the only change is instead of 2 inches, we have 1 inch because we are considering the symmetry condition. And for the third spring, it will be E times 10 inches by 1, right? And this is divided by the length of that spring, which is, or what is represented as spring, which is 4 inches.
Sorry, so Leonardo, for the area, what is it? 1 inch.
The area is 10 by 1, right? Oh, no, sorry. We're using symmetry. It's true. So it would be 5 by 1.
5
by 1 over 4.
So the way you came up with that is that this length here is 16. From here, from point O to this point is 16.
Yes.
From this point to this point is
12.
12.
So we have 4 left, right?
So the height.
So, and the height is 16. The height is 10. The height is 10, right? The height is 10 divided by 2.
Right. The height is 10. So half
divided
of
by
that
2 would be 5. Yes, half of that. So it would be 5, right?
And the length?
It would be 4.
4, yeah.
Yeah, 4 inches.
I guess we're ready for the element code numbers, huh?
Yes. So now we can represent, let's put the first element. And the first element is has 2 nodes, right? Which is 0 and 1.
So you're talking about element number K1, which is connected by this and that, right?
Yes, correct.
So that's 0, 1.
0, 1. For the element 2, we have 0, 1 as well. And for the element 3, we have 1 and 2.
Okay.
Now we're going to proceed to construct the global stiffness matrix. So the global stiffness matrix is of the size, if a matrix of the size of the active nodes. So if we have only 2 active nodes, it means that the size of the matrix should be 2 by 2, right? So for the element 1, the stiffness matrix, which is 2 by 2, according with the convention we use for the degrees for the active nodes or the displacements, we have this 0, 1 for the rows and 0, 1 for the columns. And for the third element, we have 1, 2 rows, 1, 2 columns. So now we go to the global matrix, and since this and we only look for the combination or the nodes related with the active nodes. So the first one is from K1, let's look at the position 1, 1. And the position 1, 1 will be the stiffness K1 times 1. So let's look in the element 2, what is the value for that position 1, 1? Is K2. So we add them up to K1. And let's look to the element K3, which is the position 1, 1. So we just need to add them up K3. So now we have the component 1, 1 in the global stiffness matrix. If we repeat the same procedure for the other nodes or active nodes, we can see that for the position or the combination 2, 1, we have minus K3, right? If we look, the position 1, 2 is minus K3 as well. And now if we look at the position 2, 2 is K3. You can see now, you can verify that if what you did is right, the global stiffness matrix should be symmetric, right? Which it is. Now we can go to the representation of the linear system. We have two active nodes, so D1 and D2, and on the other half of the equality, we have the external loads. All right, because this is all at the global level, it's not at the element level. So we need to include the forces, and the only force that we have in this structure, it happens at the third node, where D2, or where we have the displacement number 2, or the second active node. Since we are considering symmetry, and I think this is related with a question I got at the beginning. Since we are considering symmetry of the problem, we're going to solve the problem by P over half, not P instead of P, right? So the fact that we are considering half of the structure and the half of the structure is loaded by half of the total load, when we solve for P, we are solving for the system. We are solving for the load for the entire structure, right? Okay. So now getting back to the matrix representation. The question is, how can we solve for that system, right? We have three unknowns: D1, D2, and P over 2. What is the value for P2? We can just leave it like P2. Sorry, P over 2. Sorry. Just consider that since we're doing by hand, we can just do leave the solution of D1 and D2 in terms of P over 2.
Or Leonardo, since the question is asking what is the maximum load the structure can sustain, and we need to get to 50 KSI, perhaps you apply a fake load. So apply a fake load of P equals 1, and then determine the deflections D1 and D2. Find deflections D1 and D2 for this load. And once you have those deflections, we can find the forces. We can find the forces acting in each of these sections. And then we can find the stress. And then all we have to do is scale this load up until the stress reaches 50 KSI. What do you think?
Yeah, definitely. That's exactly what you mentioned before, right? So yeah, that would be the approach.
So I guess we solve for D1 and D2, right? With that load of P equals 1. And how do we find the forces inside the springs? We have to use a local, this stuff.
We need to get back, exactly. We need to get back to at the local level. And as we represent in this isolated spring, at each node, we have also an equation, right? That equation at the local level is pretty much, we can have that K times the displacement, the difference between the displacement. So let's take for example, the first element.
Yeah, let's do that. So element number 1. So I solve, let's say for a load P equals 1, we solve for D1 and D2. We already know the answer for that. So then we go to element 1. What do we do, Leonardo?
So for
Right.
element one, and the displacements will be 0
0
and 1.
and D1. We know this one because
And
we
D1
solved.
and D1 and D1, right? Which is
Mhm.
known at this point.
So just multiply these two things.
And that should be equal to the force at node I for the element 1 and force at the node J for the element 1.
Which should be equal and opposite, actually.
Both are, for convention, both are pointing to the right, right?
Mm-hmm. Yeah, but when you solve it, I think you're gonna get the same magnitude, but the signs will be different.
Oh, yeah, of course.
So then you can get the forces, right, Leonardo? Because I know K1, I know 0, I know that's 0, I know D1 because I solved it earlier, right?
Yes.
So then I can calculate the stress. So I can calculate sigma 1, sigma, the stress. So stress in spring 1 is going to be what? Is going to be either of these forces, doesn't matter which one you select, is going to be the same. FIE divided by the cross-sectional area A for element 1. Right, Leonardo?
Yeah.
And then we do it for spring 2.
And that in that case, we have the D1 and D2.
I think it's the same
I know
way.
that's 0, 1, 0, D1, 0, D1.
Same way.
Sorry, I was thinking in the number 3. We have
So stress in spring 2 gives you FIE divided by A2. And then we have to do it for spring 3, right?
correct. Now the displacements here are from the active nodes D1 and D2.
And I know these ones because I solved for it earlier. For the load of equal P equals 1. So I get like the stress for each spring. Then I can figure out which spring is more critical, right? Like whatever stress is highest, right?
And exceeds the allowable.
Well, it's not going to exceed because I'm applying a very small load of P equals 1.
Oh, yeah, I forgot you were proposing to do it that way. Yes, it's true.
So then we have to, one of the questions that came up in the chat is we should design to 50 KSI divided by 1.5. How much is that? There's a calculator here. $33. So all you have to do, I think the stress is going to be the same here and here. Just looking at the problem visually. And it should be more critical than here because this one is more cut. So more force, I think there will be more stress here and here and here, right? Than here. Did I lose you guys? Hello?
That's not for me, guys. It's for you. You are part of this.
Right.
You are part of this discussion too.
But that's what you're gonna find.
One second, Vinny. 1 second, Vinny. Could you get back to the previous slide? So, I mean, this is not anything related with finite elements. This is coming from your knowledge of strength of material. So what do you think about what Professor Goyal mentioned about what area of this structure is the weakest one?
Yeah, probably where the material is missing, since we have a shorter or smaller cross-sectional area for the force being applied as compared to where node 3 is.
So the area connecting, you mean the area connecting the node 2 with the node 3? That's what you mean?
No. I was comparing, so where the professor drew, you know, like the red lines on the left, where there is material, where the material is cut out. I feel because there's a smaller cross-section area there, we would have a higher stress in that area.
Yeah.
Excellent. Excellent.
Yes.
So let's say this stress, when you do the whole thing, this stress comes out to be some stress S, right? So that's going to be more critical, and that should be equal. Just visually looking at it, seems to me, visually looking at it, seems to me it's going to be equal. So then you can, you know, if for P equals 1, you get a stress of S, then what load is going to give you a stress of 33 KSI. So you can scale that up, right? You can scale that up. So 1 divided by S equals, and I can solve for P. You know this number, you're going to find it. So P is going to be 33 KSI divided by S. So that's how you can find a load that fails it. And then somebody's saying that spring 2 will have somebody's saying that maybe spring 2 is the one that fails first. I don't think so, because the K also is different. The K is also smaller because we cut it in half. So it's gonna be, I think it's gonna be the same. But you should try it. Try it to see what you get. You're gonna have to do this in ABAQUS anyway. We already have the tutorial, you can check it out to see what the answer was. Because the same problem was solved in ABAQUS, and the tutorial was posted. Should we move to how to do the energy one quickly?
Yeah, I think so. It's a good idea.
I think we finished it. We finished this problem already.
Yeah, it's done. Okay, so for the energy, I mean, we already have what we already idealized the structure by these springs. We already identify what are the active nodes, right? So now what we want to do is to calculate the total potential energy of the structure, and the total potential energy of the structure comes from the contribution of the energy of each segment represented by the spring. So we have a total pi for this specific case that's representing the total potential energy, right? And we have 3 springs, so it means that we have the total contribution of that would be pi 1 plus pi 2 plus pi 3, right? And if we just in the general case, if we have some external work, we need to subtract it to this to the right hand side, just in we have it, right? Okay, so now the problem goes to what is the value for the potential energy from the first element. So we just need to apply the formula, right? We have that this k d squared over 2, right? And since we have the values of the displacements at each node, this distance, this x squared or d squared is known at this point. And the external load, or the energy due to the external load, is due to the external load, right? And the external load is P over 2, because remember that we are considering the symmetric case, and we multiply this by the distance at that node, which is D2. Okay? All right, so now the next step is we need to minimize this, right? So when we minimize, this energy, we take the derivative with the partial derivative of the total potential with respect to the displacement at each node. So the first one would be the partial derivative with respect to D1, right? The second one would be the partial derivative with respect to D2, right? And you can see we have two equations. We have two unknowns. We can solve for the displacement, right? All right. How can you verify that you make it right? Because the solution should be the same as what you got on the first part. So yeah, I mean that's the procedure applying energy